Welcome to this pre-class video on alkenes, alkynes, and aromatic compounds. Well, when you look at a molecule, you need to be able to say or predict which classifications it belongs. And so three important classifications are presented here. So for example, an alkene. If you have an alkene, then you have at least one carbon-carbon double bond in the molecule, or vice versa. If you see a carbon-carbon double bond in the molecule, then you know that at least one classification of the molecule can be alkene. And in terms of naming alkenes, they end in E-N-E. Alkynes. Well, these are related to carbon-carbon triple bonds. If you have a carbon-carbon triple bond in a molecule, then one of the classifications is going to be an alkyne, and then that in the name it's going to be Y-N-E. Now, aromatic can be a lot of different things, but in our world, we're going to narrow it down to what we call just a benzene ring. Does a molecule have a benzene ring? And if it does, we're going to call it aromatic. Well, what does that mean? Well, you have 6 carbons in a cyclic structure. In 2 dimensions, think of it being a hexagon. And then you have 3 alternating carbon-carbon double bonds. But these carbon-carbon double bonds are special. That's why we just don't call this an alkene. We call it aromatic. And of course, I've kind of drawn this as a skeleton structure. You know that at each intersection of lines is a carbon atom. And of course, I've drawn the shorthand notation. So each one of these carbons, to get 4 bonds, has an understood hydrogen there. Now, you can make derivatives of the benzene ring by replacing some other atom or groups for a hydrogen off of benzene, and you can get a wide variety of compounds. Well, one of the things we want to be able to do is name alkenes, and you name alkenes in a very similar manner to how you named alkanes, and we have gone over those rules, and you should know those rules. In naming alkanes, you were first to find the longest continuous chain of carbons the longest continuous chain of carbons, and then you numbered it to make the branch points as low as possible. Here there's another rule. Yes, you want to find the longest continuous chain of carbons, but it must include the carbons of the carbon-carbon double bond. So here's an alkene, and I've drawn it in kind of a condensed structure, and this is a legitimate molecule. We want to find the longest continuous chain that contains the carbon-carbon double bond, and oh, by the way, we need to number it such that the carbons of the carbon-carbon double bond are the lowest numbers possible. So you can see, let's start here as number 1, number 2, number 3, number 4, and number 5. Now you could have made this carbon number 1, and that would have been okay, because these two are equivalent methyl groups, if you will, or equivalent carbons, let's just say that. And you also know that anything not in the parent chain or the longest continuous chain has to be in a substituent, and this is one of the substituents you have to know. This is on the playbook. This is methyl. Well, when it comes to assembling the name, you have to name the substituents, make sure each substituent has a number in front of it so we know where it's at, and then go from there. Well, also this is going to have 5 carbons in the longest continuous chain, or the parent chain. So it's going to be based on pent, P-E-N-T, because we have 5 carbons. So it looks like we're going to have 2 methyl, and that's the only substituent we have. So now let's go to the parent chain. Now this next step is important though. You have to, in the name, you have to provide the lowest numbered carbon that's in a carbon-carbon double bond, so we can locate it in the molecule. So this would be 2, because of right here it starts at carbon 2, and then we have 5 carbons pent, and then it's a double bond, or it's an alkene, so it's pentene. 2-methyl-2-pentene. That's how we would name this molecule. Well, let's talk about naming alkynes. A similar type of thing. Find the longest continuous chain that contains the carbon-carbon triple bond, and then when we number it, we have to make the carbons of the triple bond the lowest numbers possible. So I'm going to go 1, 2, 3, 4, 5, 6. Everything is included except this group here. This is our old friend fluoro. Note the spelling. And so now we have everything in a longest continuous chain, and we're ready to write the name. So this is going to start out for fluoro, and we have to include a number for the triple bond starts. 3. There's 6 carbons. Oh, wait a minute. That's not 3. It's the lowest one. The lowest of these two numbers is what we need. So it's 2-fluoro 2. There's 6 carbons. That's hex. It's an alkyne. Y-N-E. Again, you may have wanted to number from this end. That would make the fluoro the lowest number, but that's not the rules. When you have a multiple bond, a double bond or a triple bond, that takes precedent over any substituent in terms of numbering to get the lowest combination of numbers. Alright, well, with alkenes, there's another little issue that's terribly important in terms of their structure, function, and naming. Let's just look at a carbon-carbon double bond, and sometimes it's going to be a good idea just for you to kind of like label those special carbons. Hey, when you have an alkene, the carbons of the carbon-carbon double bond are special. Okay? So, what we know is we can have what we call geometric isomers. And isomers are compounds that have the same molecular formula but a different three-dimensional arrangement of atoms. So when can you get these geometric isomers? Well, we saw them in cyclic alkanes. We saw cis and trans. Well, we can get cis and trans with carbon-carbon double bonds as well. So basically, what do you need to do this? Well, you need an atom or group on carbon A that's the same on carbon B. So typically, but not always, this will be like a hydrogen. So there's a hydrogen on carbon A and there's a hydrogen on carbon B. And then it doesn't really matter what the rest of the molecule is. Those two hydrogens, there's one on A, there's one on B, but they are locked on opposite sides of the double bond. That's because you cannot rotate around a carbon-carbon double bond like you can a carbon-carbon single bond. So these hydrogens are locked in an opposite arrangement. This is called trans. They are on opposite sides of the double bond, and they will always be that way. Always be that way. Okay? Now, you can have another molecule with the same connections of atoms, where if this is carbon A and this is carbon B, you can put hydrogen here on carbon A and a hydrogen here on carbon B, and it's like, oh, wait a minute. This molecule will have the same formula as the one above, but the arrangement of the two hydrogens on the carbons of the double bond are different. Three-dimensionally, they're different. They are locked on the same side of the double bond. And this is what we're going to call a cis isomer. Ladies and gentlemen, cis and trans isomers are different molecules. They have different properties. And so that's why we have to go to the trouble to recognize these differences. Well, when is this going to come up in terms, for example, of naming? Well, if I give you enough information, sometimes you can predict whether we have the cis or trans isomer. Look at this molecule. First of all, you know it's an alkene because you see this prominent carbon-carbon double bond. So hey, I'm going to label the carbons just for discussion. And it looks like carbon A has a hydrogen and carbon B has a hydrogen. Well, that means there can be cis-trans isomerism. You can have cis-trans isomers. Well, which isomer is it? Well, it looks like the hydrogens, the common atom in this case, on A and B, they are locked on opposite sides of the double bond. So we clearly have a trans isomer. Now, what we do next is just simply do what we've always done, well, since this video started, in terms of naming alkenes. So we want to find the longest continuous chain, including the double bond, make the double bond the lowest number possible. So we have 1, 2, 3, 4, 5. It looks like we have another pent because we have 5 carbons in the longest continuous chain. Here's an old friend bromo. It's a substituent we need to know. And so we have everything we need to name this now. And when you start naming these, you put this special prefix, cis or trans, first. So this is trans 4-bromo. Where's the double bond start? 2. How many carbons in the longest continuous chain? 5. Is it an alkene or alkyne? It's an alkene. Trans 4-bromo 2 pentene. Now this can even get a little bit more complicated because sometimes we just draw the straight up skeleton structure. And when you see this, it's like, oh, okay, I know this. Every terminus is a carbon, and at every intersection of lines is where a carbon atom is located. And you see a carbon-carbon double bond in this structure. But the hydrogens aren't shown, but you know they are there. So let's just identify carbon A and B. And again, I'm just making this A and B randomly. I'm making this A instead of B just randomly, but these are the 2 carbons we have to label as either A or B. Okay? So what I know is that carbon-carbon double bonds are trigonal planar. So when I start to add the hydrogen, where I put it matters. I know for this to be trigonal planar, this has to be out this way, because carbon B is trigonal planar. There's 3 things around it, and they're all in the same plane. So this hydrogen has to be there, this hydrogen has to be there. And so basically, I've given you enough information of drawing the hydrogens, and then you look at them and you say, clearly, this is the cis isomer. Okay? Well, let's just do what else we normally do now. This is carbon 1, 2, 3, 4, 5, 6, 7. So we've got everything we need to know, well, almost everything. This is a substituent. That's a substituent. These are chloro substituents, and so we've got to put them in the name and they're both on carbon 4. And remember, every substituent gets a number. Don't shortchange a substituent, right? So let's start out. We're going to start out as cis, and then we have 4,4-dichloro. And you say, now, where did this come from? Well, you've got 2 chloros. The prefix for 2 is di, and every substituent gets a number. So you have to say 4, 4. So cis 4, 4, dichloro, and it's 2. Now every double bond we've had so far started at 2 today, but that's just random. They're not always at carbon 2, so don't get that impression. But we have 2 here, and we have 7. 7 is hept, H-E-P-T, and we have a double bond, so it's E-N-E. So this molecule is named cis 4,4-dichloro-2-heptene. I hope this video was useful for you as a precursor to what we're going to talk about in class. Thanks.